right now, as you're listening to this, your jawbone is literally melting and rebuilding itself.
Yeah, it's a fairly wild concept to start with, isn't
It
it?
really is. I mean, every single time you chew a piece of food, the mechanical stress of your teeth just, grinding together, it sends these microscopic signals into the surrounding bone.
Exactly. And those signals, they activate specialized cells that dissolve the solid bone on one side of the tooth root while simultaneously triggering other cells to essentially 3D print fresh new bone on the opposite side.
So your skeleton isn't just some, I don't know, static, dry scaffolding holding you up. It is a completely shape-shifting, living organ.
And that dynamic, ever-changing nature is precisely why we can't look at the human body as just a collection of inert parts.
Right.
To truly understand the architecture of the head and neck, we have to start by understanding the rules of the metropolis.
The metropolis. I like that framing.
Yeah, if you imagine the body as a sprawling, ancient, yet highly advanced city, the individual cells, they are the citizens in the bricks. The tissues are the distinct neighborhoods, each with a very specific character.
Okay, yeah.
The organs are the civic centers and factories. And the organ systems, which is really our focus today, they are the vast infrastructure networks. The transport grids, the defensive walls, the communication lines.
So whether you are a medical student laying down your foundational knowledge or a surgical or dental trainee revising your applied anatomy, or honestly just someone fascinated by how we are put together, we are taking you on a deep dive today. We are exploring Chapter 3 of the textbook of Head and Neck Anatomy by Hyatt and Gartner.
And I think the anchor for our entire journey today is this. Anatomy is the study of structure in service of function.
Right, and how that structure shapes disease, intervention, and outcome.
Quite right. We aren't here to just rattle off a list of Latin terms for you to memorize by rote.
God, no. That would be awful.
It would. We are here to build your spatial and functional mental models. Because if you attempt to memorize the regional anatomy of the neck without understanding the underlying systems, the integumentary, muscular, skeletal, circulatory, and nervous systems, you're really just staring at a static map.
You'll know the names of the roads, but you won't understand the traffic.
Spot on. We want to transform that map into a living, dynamic network. Every single structure we will eventually cover in the head and neck, it exists entirely within these systems.
So they receive blood, they respond to electrical nerve impulses, they are leveraged against bone, they're moved by muscle, and they are defended by skin.
Exactly.
Well, let's start at the absolute borders of our metropolis then. The city walls, the integumentary system. I think the temptation is to view the skin as a sort of passive wrapper, like biological shrink wrap, just keeping our internal organs from spilling out onto the floor.
Yeah, that's a very common misconception.
But looking at the source text, this is a highly active, aggressively defensive interface.
It is. The integumentary system, which encompasses the skin, the hair, the nails, and the various glands, is arguably our most versatile organ. It's a dynamic boundary.
Right.
Yes, it protects against physical intrusion and the loss of moisture from within, but it's also this massive sensory receptor array, a vital temperature regulator, and a really complex organ of secretion.
And to understand how it does all this, we have to look at how the walls are actually layered. Let's start with the outermost layer, the epidermis. This is made of what the textbook calls stratified, squamous, keratinized epithelium.
It's quite a mouthful.
It is a very dense piece of academic terminology. But if we break it down based on function, stratified just means it is layered. Squamous means the cells are flat and sort of scale-like.
Yeah.
And keratinized means they are packed full of a tough, waterproof protein.
That is a perfect functional translation. And what makes the epidermis so fascinating is that it is entirely avascular.
Wait, meaning no blood supply at all?
None. There are no blood vessels in this outer layer. The cells rely entirely on oxygen and nutrients, just diffusing upwards from the layer beneath it.
Which sets up this incredible cellular journey. The text notes the deepest layer of the epidermis, sitting right on the basement membrane, is called the stratum basal, or historically the stratum germinativum.
The germinating layer. The factory floor, if you will.
Right. The cells here are constantly dividing, pushing the older cells upwards toward the surface.
And as those cells are pushed away from the blood supply below, their environment changes. They begin to produce a substance called keratoisin.
Okay.
As they migrate further up, that substance transforms into mature keratin. By the time these cells reach the absolute outermost surface, the stratum corneum, they are completely dead. They're essentially just flattened bags of tough protein.
So the very outer layer of our city wall is just a sacrificial barrier of dead matter.
Absolutely. We are constantly shedding it and replacing it from below. And the text notes that the thickness of this dead stratum corneum is directly proportional to the amount of physical trauma or friction it experiences.
Form in service of function again.
Exactly. If you look at the palm of a manual laborer, the stratum corneum is immensely thick, creating a callus. The body senses the mechanical stress and ramps up production on the factory floor to reinforce the blast doors.
But below those blast doors, we hit the dermis, and this is where the logistics of the wall are actually managed.
Yes, the dermis is the vascularized connective tissue layer. This is the life support for the epidermis. It houses the intricate capillary beds, the lymphatic drainage channels, and the dense network of nerve endings that give us our sense of touch, pain, and temperature.
It is also where we find the embedded infrastructure, right? The sebaceous glands, sweat glands, hair follicles.
Up on.
Now, if I picture these two layers, the dead, scaly epidermis sitting on top of the living vascular dermis, they don't just meet at a flat line, do they? The text describes them interlocking.
Oh, they interdigitate aggressively. The dermis projects upwards in little microscopic hills called dermal papillae.
Okay.
And the epidermis projects downwards in epidermal ridges. Think of two pieces of egg crate foam pressed together.
What's the functional reason for that? Is it just to stop the skin from peeling off?
Primarily, yes. It vastly increases the surface area of the connection, securing the two layers against shearing forces. If you scrape your arm against a rough brick wall, that interlocking architecture prevents the epidermis from just sliding right off the dermis in a single sheet.
Wow. Okay.
But nature is incredibly efficient and often uses one structure for multiple purposes. On our fingers, palms, and soles, these epidermal ridges are highly pronounced and organized into complex whorls and loops.
Fingerprints.
But, evolutionary biology didn't give us fingerprints to help detectives solve crimes or to unlock our smartphones.
Right, obviously.
Those pronounced ridges provide vital friction. They give us the mechanical grip necessary for walking upright without slipping and for grasping complex tools. Furthermore, the ducts of our sweat glands open right at the summits of these ridges.
Oh, wait. So they sweat directly onto the ridges?
Yes. They provide a microscopic amount of moisture to the ridge, which slightly increases the surface tension, enhancing the grip even further.
It's literally like licking your finger before turning a page in a book. It's built-in grip enhancement. That is brilliant.
It really is.
That brings us to the deepest layer of the city walls, the basement level, the hypodermis or the subcutaneous tissue.
Anatomically, this is also referred to as the superficial fascia. It is a layer of loose connective tissue, and it is the primary storage site for our body's adipose tissue, or fat.
Right.
Clinically, large deposits of this fat are referred to as the panniculus adiposus. It serves as thermal insulation and a vital mechanical shock absorber.
I want to look at how radically this varies depending on where you are in the body. The source text points out this extreme contrast. The skin on your back or the sole of your foot can be up to 6 millimeters thick, packed with this dense fat and connective tissue.
Yes.
But the skin on your eyelid is a delicate 0.5 millimeters thick, and it is entirely devoid of subcutaneous fat. It's like comparing the blast doors of a bunker to a delicate stained glass window.
Which is a beautiful example of local adaptation. I mean, you need that thick, fat-padded shock absorber on the sole of your foot to handle the immense kinetic energy of walking or running.
Yeah.
But if your eyelid possessed a thick layer of fat and dense fascia, the mechanical resistance would be too great. You wouldn't be able to blink rapidly enough to clear debris or distribute tears across the cornea. You would go blind.
And if we tie this directly to the head and neck, the core focus of our trainees listening, the hypodermis in this region has a highly unique evolutionary adaptation.
It does. In most other mammals, such as a horse or a dog, you'll find a thin sheet of voluntary muscle embedded right in the hypodermis. It's called the panniculus carnosus, and it allows them to rapidly twitch their skin to shake off flies or parasites.
Right. You see horses do that all the time.
Exactly. In humans, that widespread sheet has largely regressed. But in the head and neck, we have retained it, highly evolved it, and repurposed it.
We repurposed fly-shaking muscles into the muscles of facial expression?
Precisely. To understand why this is unique, you have to look at normal skeletal muscle. A typical muscle, like your bicep, originates on one bone, crosses a joint, and inserts onto another bone. When it contracts, it moves the joint.
Okay.
But the muscles of facial expression originate in the bone, or the deep fascia, and they insert directly into the skin, into the dermis itself.
So they don't move joints at all. They just pull the city walls, they wrinkle the integument.
And that subtle biomechanical difference is the absolute foundation of human nonverbal communication. Every micro-expression, every smile, frown, or look of surprise is achieved because these specific skeletal muscles are anchored directly into our biological boundary.
That is fascinating. Before we leave the walls, there is a quirky little clinical detail mentioned in the text regarding the glands. Fordyce granules.
Ah, yes. Sebaceous glands usually exist to secrete sebum, an oily, lipid-rich substance, directly into a hair follicle. It coats the hair and spreads over the skin to keep it pliable and waterproof. But Fordyce granules are ectopic sebaceous glands.
Ectopic meaning there are somewhere they usually aren't.
Yes, they're fully formed sebaceous glands that exist in areas completely devoid of hair. You will frequently find them on the vermilion border of the lips, or even inside the oral cavity on the buccal mucosa, the inner lining of the cheeks.
What do they look like?
They appear as tiny, painless, pale yellow or white spots. For a dental or medical trainee, recognizing these is crucial because they are a completely normal anatomical variant. They serve no functional purpose, but they mimic the appearance of certain pathologies. Recognizing normal variation is the first step in diagnosing disease.
So we have the defensive walls established, but a static city is a dead city. We need the engines that move the infrastructure. Let's explore the muscular system, the functional integration of movement. We have 3 entirely distinct types of muscle tissue to work with.
Yes, skeletal, cardiac, and smooth muscle. All 3 are comprised of specialized cells that possess the capacity to forcefully contract.
Okay.
But their microscopic architecture is brilliantly tailored to the specific functional demands placed upon them.
Let's start with the automated systems. Smooth muscle. If I'm looking at this under a microscope, what am I seeing and what is it doing?
You are seeing cells that are fusiform spindle-shaped, tapering at both ends. They are non-striated, meaning they lack the highly organized banded appearance of other muscle types, and they possess a single, centrally located nucleus.
Right.
Crucially, they are completely involuntary. You cannot consciously command smooth muscle to contract. It is governed entirely by the autonomic nervous system.
So where are these automated engines running?
They form the contractile walls of our viscera, our internal organs. In the gastrointestinal tract, they are arranged in outer longitudinal and inner circular layers. When they contract in a coordinated wave, they create peristalsis, the physical force that pushes food from the esophagus down through the intestine.
Wow.
But they're also ubiquitous in the circulatory system. They line the walls of our blood vessels. By contracting or relaxing, they alter the diameter of the vessel lumen, which is how your body instantaneously regulates blood pressure and directs blood flow to where it is needed most.
You mentioned hair follicles earlier. Don't they have a smooth muscle component?
They do. The erector pili muscle. It's a tiny band of smooth muscle attached to the base of the hair follicle. When you experience cold or intense emotional stress, the autonomic nervous system triggers that muscle to contract.
And it pulls the hair perfectly upright.
Exactly. In a densely furred animal, this traps a layer of insulating air to preserve heat, or makes the animal appear larger to a predator. In humans, we lack the dense fur, so we just get goosebumps. It's a vestigial reflex driven by smooth muscle.
Which brings us to the second involuntary engine, cardiac muscle, confined strictly to the heart.
Like smooth muscle, it is involuntary, and it generally features a single central nucleus. But unlike smooth muscle, cardiac tissue is highly striated.
Getting striped.
Yes, the contractile proteins inside the cell actin and myosin are arranged in perfectly overlapping repeating units called sarcomeres, which gives it a striped appearance under magnification.
But the heart can't afford to have its cells firing randomly. I mean, it needs absolute rhythmic perfection. How does the architecture of cardiac muscle guarantee that?
Through an evolutionary masterpiece called the intertalated disc. Cardiac muscle cells do not just lie parallel to one another, they branch and anastomose, fusing together into a massive three-dimensional web.
Okay.
The physical point where the end of one cardiac cell meets the end of another is the intercalated disc.
And what happens at that junction? Why is it so special?
These discs contain gap junctions, actual physical pores connecting the cytoplasm of the 2 adjoining cells. This means an electrical impulse doesn't have to navigate a complex chemical synapse between every single cell.
It just flows straight through.
Exactly.
Sure.
The entire network of cardiac muscle acts as a functional syncytium. When the pacemaker fires, the wave of electricity spreads instantaneously across the tissue, ensuring that millions of individual cells contract in one beautifully synchronized, powerful squeeze.
That leaves us with the heavy lifting, the skeletal muscle. This is what we use to actually interact with the external world.
Yes. Skeletal muscle represents roughly 40% of an adult's total body weight. It is highly striated, and unlike the other two, it is under conscious, voluntary control.
The cellular structure here is wild. The text points out that a single skeletal muscle cell, a muscle fiber, is multinucleated, and those nuclei are shoved all the way out to the extreme edge of the cell membrane.
That's right. During embryonic development, hundreds of individual precursor cells, called myoblasts, fuse together to create one single, massive muscle fiber. Because they fuse, the resulting supercell retains all of their nuclei.
And why are they shoved to the edge?
To make room. Those nuclei are pushed to the extreme periphery to make room for the thousands of rod-like myofibrils that pack the interior of the cell. These myofibrils are the actual molecular ratchets that generate force.
But a muscle isn't just a loose bundle of these giant fibers, is it? It has a highly specific architectural hierarchy. It's built like a structural suspension cable.
The organization is immaculate. Let's trace it from the micro to the macro. You start with that individual multinucleated muscle fiber. That single fiber is wrapped in a microscopic, delicate sheath of connective tissue called the endomysium.
The first layer of insulation.
Yes. Next, the body takes a group of these individually wrapped fibers and bundles them together into a package called a fascicle. That fascicle is then wrapped in a slightly thicker, tougher connective tissue layer called the paramecium.
Right. And then all of those fascicles are bundled together to form the actual belly of the muscle that we can see with the naked eye.
And that entire gross muscle is encased in a dense, tough, outer layer of connective tissue known as the epimysium, which is contiguous with the deep fascia.
Let's hold on that term, deep fascia, because for surgical trainees, this isn't just anatomical trivia. This is life and death compartmentalization. Why does the deep fascia matter so much?
Functionally, the deep fascia creates a frictionless surface, allowing powerful muscles to slide forcefully past one another without tearing. But clinically, the deep fascia forms tough, unyielding compartments that wrap around muscle groups and attach directly to the bone.
Okay.
Because these fascial sheaths are so dense, they act as highly effective physical barriers against the spread of infection or fluid.
So if a severe infection starts in a specific muscle compartment in the neck, it can't just easily soak through to the neighboring muscles.
Exactly. The infection is trapped within the fascial plane. However, this is a massive double-edged sword.
Why?
Because the deep fascia is unyielding. If bleeding or severe swelling occurs within that compartment, the pressure has nowhere to go. It builds inward, eventually crushing the blood vessels and nerves within the compartment, leading to tissue death.
Oh, wow. Compartment syndrome.
Precisely. And understanding the exact borders of these fascial planes dictates where a surgeon must cut to relieve the pressure. Furthermore, in the head and neck, certain fascial planes run uninterrupted all the way down into the mediastinum, the chest cavity containing the heart.
Wait, really?
Yes. If a severe dental infection accesses one of these specific planes, the bacteria can ride that anatomical highway straight down into the chest, which is a lethal emergency. Anatomy dictates the pathology.
So we have these heavily wrapped, compartmentalized cables of muscle, but to move the city's scaffolding, they have to attach to the bone. How does a soft tissue muscle grip a hard piece of bone?
Well, the muscle fibers themselves don't touch the bone. At the very end of the muscle belly, the contractile fibers stop. But all those layers of connective tissue we just discussed, the endomysium, the paramecium, the epimysium, they continue on.
They sort of weave together.
Exactly. They merge into a dense, incredibly strong band of regular collagenous tissue. This is a tendon.
And the tendon anchors to the bone.
It doesn't just glue itself to the surface. The collagen fibers of the tendon physically weave themselves directly into the periosteum, the outer fibrous layer of the bone, and even penetrate into the underlying calcified bone matrix itself. It's a profound structural integration.
But the textbook notes that not all attachments are cord-like tendons. Sometimes we see aponeuroses. What's the difference?
It comes down to the required distribution of force. A tendon is cord-like. It concentrates the force of the muscle into a single, highly specific focal point on the bone. But some muscles are broad and flat, and they need to pull evenly across a wide area.
Right, they need a wider grip.
In these cases, the connective tissue extends as a broad, flat, pearlescent sheet. That sheet is an aponeurosis. A prime example in the head and neck is the epicranial aponeurosis, the broad sheet of dense connective tissue that connects the frontal muscle of the forehead to the occipital muscle at the back of the skull.
Spanning the entire roof of the head.
Yes.
Okay, pulling these high-tension cables back and forth over hard bone creates massive friction. How do we prevent the tendons from fraying like a rope dragged over a rock?
Through the deployment of biological lubrication systems. In high-friction areas, the body places a bursa. A bursa is a small, flattened sac lined with a synovial membrane and filled with a tiny amount of highly viscous synovial fluid.
Like a liquid ball bearing.
Exactly. Placed exactly between a tendon and a bone, or between two muscles, allowing them to glide smoothly.
And what if the tendon has to pass through a tight anatomical tunnel, like in the wrist or ankle?
And the bursa isn't enough. The body uses a synovial tendon sheath. Imagine taking a bursa and wrapping it completely around the tendon, forming a double-layered tube. The inner layer sticks to the tendon, the outer layer sticks to the surrounding tissue, and the synovial fluid sits between the two layers.
So the tendon can now slide back and forth powerfully within this perfectly lubricated sleeve, form dictating function again. Let's talk about the physics of generating that power. The source material explains that the internal architecture of the muscle, the direction the fibers run, determines how strong it is versus how far it can contract.
This is fundamental biomechanics. If you need a muscle to have a massive range of motion, the individual muscle fibers will run parallel to the long axis of the muscle, straight from origin to insertion. The sartorius muscle in the thigh is a great example.
Long parallel fibers mean maximum shortening distance.
Yes, but relatively low total power, because you can only fit so many parallel fibers into a given cross-section.
But what if I don't care about range of motion? What if I just need raw, brutal crushing power? Say, for the jaw muscles when chewing.
Then you abandon the parallel architecture and employ a pennant arrangement. Pennant means feather-like. Instead of running straight, the tendon runs down the middle of the muscle, and the shirt muscle fibers attach to the tendon at an oblique angle.
Like the barbs attaching to the quill of a feather?
Exactly. Because they are at an angle, you can pack significantly more individual muscle fibers into the exact same spatial volume. More fibers mean more contractile units pulling simultaneously.
And there are variations of this, right? Unipennant, bipennant.
Yes. A unipennant muscle has fibers entering the tendon from one side. A bipennant muscle has them entering from two sides, like a complete feather. And a multipennant muscle, like the deltoid in the shoulder or the masseter in the jaw, has multiple tendons with fibers weaving in from complex angles.
So the trade-off is a much shorter range of contraction, but an exponential increase in raw kinetic power.
Exactly right.
Okay, wait, hold on. I need to push back on something regarding how these fibers actually fire.
Okay.
The text clearly states that skeletal muscle fibers obey the all or none law of neurophysiology, meaning if a nerve stimulates the fiber, it contracts at 100% maximum capacity every single time.
That is correct. An individual muscle fiber cannot contract at 50% power. It is an absolute binary event, all or nothing.
Okay, but if that is true, how do I pick up a delicate paper coffee cup without instantly crushing it into pulp? If the fibers in my forearm are firing at absolute maximum capacity, I should just be slamming my hand closed violently every time I move. How do we achieve nuance?
That is a brilliant question, and it strikes at the very heart of motor control. The nuance is not achieved by changing how hard a single fiber pulls. The nuance is achieved by controlling how many fibers pull. This introduces the concept of the motor unit.
The motor unit. Okay, break that down for me.
A single motor neuron, a single nerve cell leaving your spinal cord, travels to a muscle. But it does not connect to every single fiber in that muscle. As it enters the muscle belly, the nerve axon branches out, and it connects to a highly specific subset of scattered muscle fibers.
Right.
That one neuron, plus the specific squad of muscle fibers it commands, constitutes one motor unit.
So when the brain fires that one neuron, only that specific squad of fibers contracts.
Exactly. And while those specific fibers in that unit are contracting at their absolute 100% maximum, the thousands of other fibers in the muscle are completely relaxed. So if you reach out to pick up a delicate paper cup, your brain only recruits a very small number of motor units.
Ah, I see. So the overall force generated by the entire muscle is very low, allowing for a gentle grip.
Yes. But if you suddenly realize the cup is actually made of solid lead,
then your sensory nerves send an immediate alarm back to the central nervous system.
And your brain instantly recruits dozens, then hundreds of additional motor units. The muscle summons more and more squads into the fight, vastly increasing the overall force until you can lift the weight.
That makes perfect sense. So the precision of a muscle depends entirely on how big these squads are.
Precisely. In the massive postural muscles of your back or legs, One motor neuron might control a squad of 2,000 muscle fibers. It's a blunt instrument for gross movement. But the text points out that in the head and neck, we see the opposite extreme.
Like where?
Look at the extrinsic muscles that move the human eye, or the tiny stapedius muscle in the middle ear, which is only about 2 millimeters long and regulates the vibrations of the hearing bones.
They must have microscopic squads.
In those highly precise muscles, a single motor neuron might control a squad of only 5 to 10 muscle fibers. It requires immense neurological bandwidth from the brain, but it grants us the astonishing micro-precision required to track a moving object with our eyes or rapidly modulate our hearing.
Incredible. So the muscles can generate all this massive, highly controlled force, but without leverage, it's useless energy. They need something rigid to pull against. That brings us to the dynamic scaffolding, the skeletal system.
Yes, the adult human skeletal system comprises 206 distinct bones, alongside associated cartilage. We divide it conceptually into two territories.
The axial and the appendicular, right?
Correct. The axial skeleton forms the central longitudinal axis of the body. It includes the 80 bones of the skull, the hyoid bone in the neck, the vertebral column, the ribs, and the sternum. Its primary function is the encasement and protection of the central nervous system and the thoracic viscera.
And hanging off that central axis is the appendicular skeleton.
Yes, the 126 bones of the upper and lower limbs, plus the pectoral and pelvic girdles that anchor those limbs securely back to the axial core.
We categorize these bones primarily by their shape. Long bones like the femur, short bones like the carpals in the wrist, flat bones like the vault of the skull, and irregular bones like the intricate vertebrae. But the text mentions a couple of oddities: sesamoid bones and wormian bones. What are those?
Sesamoid bones are a fascinating mechanical adaptation. They are small, seed-like bones that develop entirely within the substance of a tendon. They form in regions where a tendon passes over a joint and is subjected to extreme pressure and friction.
Like the kneecap.
Yes, the patella is the largest sesamoid bone in the body. It grows inside the quadriceps tendon, pushing the tendon slightly away from the center of the knee joint, which dramatically increases the mechanical leverage of the muscle.
And wormian bones.
Wormian bones, also known as sutural bones, are essentially developmental anomalies. They are tiny, irregular accessory islands of bone that occasionally form within the fibrous sutures between the large flat bones of the skull.
Just extra little pieces.
Yeah, they occur when the normal centers of bone formation fail to meet and fuse seamlessly during development.
I think the biggest misconception about the skeleton is that it's just dry, dead scaffolding, like the steel girders of our metropolis. But the text makes it incredibly clear that bone is a highly active metabolic organ.
To call bone scaffolding almost does it a disservice. It is intensely alive. Beyond structural support and leverage, the skeletal system is a massive metabolic reservoir. The bone matrix stores vast quantities of vital minerals, primarily calcium, magnesium, and phosphate.
It's an emergency bank vault.
Exactly. When the concentration of calcium in your bloodstream drops, a condition that would rapidly cause neurological and cardiac failure, specialized cells in the bone instantly break down the matrix, releasing calcium into the blood to preserve your life.
And it's also a manufacturing plant, isn't it?
It is the factory for your blood. Deep within the spongy interior of flat, irregular, and short bones, as well as the ends of long bones, lies the red bone marrow. This highly vascularized tissue is packed with hematopoietic stem cell.
So it's making everything.
Every single red blood cell carrying oxygen,
Right.
every white blood cell defending you from infection, and every platelet necessary for clotting is manufactured in the marrow of your skeleton.
Which makes the process of how this living scaffold is actually built so critical. Osteogenesis. Bone development. The text details two entirely different pathways for creating bone: intramembranous ossification and endochondral ossification. And this is vital for understanding the architecture of the head and neck.
Let's start with intramembranous ossification. This is the pathway used to construct the flat bones of the skull vault, the facial bones, and parts of the mandible and clavicle.
The way I picture intramembranous formation reading the text is like 3D printing a concrete wall directly into thin air, just manifesting it from raw material.
That is a very apt analogy. In intramembranous formation, there is no intermediate model.
Yeah.
Bone forms directly within a primitive, highly vascularized embryonic connective tissue called mesenchyme.
Right.
The mesenchymal stem cells receive a chemical signal and differentiate directly into osteoblasts, the active bone-building cells.
And what do these osteoblasts actually do? How do they make bone?
They begin aggressively secreting a tough, rubbery, uncalcified protein matrix called osteoid. It's mostly collagen.
So it's soft at first.
Exactly. But because the mesenchyme is highly vascular, the blood brings in high concentrations of calcium and phosphate ions. These minerals diffuse into the soft osteoid matrix and crystallize along the collagen fibers. The matrix rapidly calcifies and hardens into solid bone.
But what happens to the osteoblasts that are pouring this concrete? Don't they get trapped?
They absolutely do. As they secrete the matrix all around themselves, they wall themselves into tiny microscopic caves called lacunae. Once an osteoblast is fully entombed in solid bone, its metabolic activity slows down and its name changes. It is now a mature bone cell called an osteocyte.
So that is the direct 3D printing method. But what about endochondral ossification? That seems like a much more convoluted pathway.
Endochondral formation is how the long bones of the limbs and the bones of the skull base develop. It is a complex, multi-stage process of replacement.
The analogy that jumps out to me here is the lost wax casting method used in sculpture. It's like carving a miniature replica of the bone out of wax and then slowly melting the wax away and replacing it with molten steel.
That is precisely what the body does, though the wax in this case is hyaline cartilage. In the early fetus, the body creates a miniaturized template of the future bone, made entirely of soft, flexible cartilage. This cartilage model grows and takes the gross shape of the final bone.
But cartilage has a critical limitation, right? It is avascular, it has no internal blood supply, relying purely on slow diffusion for survival.
Quite right. So how does the wax become steel? How does the avascular cartilage transform into vascular bone? The transformation is triggered by an invasion.
Oh, dramatic.
The outer fibrous covering of the cartilage model, called the perichondrium, suddenly becomes vascularized near the middle of the shaft. The arrival of blood fundamentally alters the local environment. The cells here differentiate into osteoblasts and lay down a thin collar of solid bone around the waist of the cartilage model, cutting off its diffusion.
Choking the cartilage inside.
Yes. The cartilage cells inside the core begin to hypertrophy, calcify their own matrix, and die. This creates an empty, calcified cavern in the center. Then the real invasion occurs. A periosteal bud, a vanguard composed of blood vessels, osteoblasts, and bone-destroying cells called osteoclasts, punches through the bone collar and invades the dead center of the cartilage model.
And they start replacing the architecture.
The osteoclasts act like demolition crews, eating away the dead calcified cartilage. Right behind them, the osteoblasts act as construction crews, laying down the true osteoid matrix, which then hardens into bone. This initial beachhead is called the primary ossification center.
And then it just spreads.
Yes. Over months and years, this process of destroying cartilage and replacing it with bone sweeps outwards toward the ends of the model until the entire structure is converted.
That cellular choreography is just astonishing. But this process of demolition and construction doesn't end when we reach adulthood. The text introduces Wolff's Law, which states that bone architecture is in a continuous state of dynamic flux.
Wolff's Law is one of the most profound clinical concepts in anatomy. It states that bone remodels itself in direct response to the mechanical stresses placed upon it.
The scaffolding is constantly analyzing the physical loads it is carrying and reinforcing itself where it is weak, while dismantling itself where it is unnecessary.
Exactly.
How does it sense that?
The osteocytes, the mature cells, trapped in those tiny lacunae act as mechanoreceptors. When a bone bends slightly under load, fluid moves through the microscopic canals connecting the lacunae. The osteocytes sense this fluid shear and signal the construction and demolition crews.
Tension versus pressure.
Exactly. If a specific area of bone experiences increased tension or stretching, osteoblasts are activated to deposit new bone, reinforcing the architecture. Conversely, if an area is subjected to constant unyielding pressure, or if it experiences complete disuse, like an astronaut in zero gravity, osteoclasts are activated to resorb the bone matrix, melting it away.
This mechanism, melting under pressure and building under tension, is the exact biological foundation that orthodontists exploit, isn't it?
It is the entire basis of orthodontics. When an orthodontist tightens a wire, it applies a persistent mechanical force to a tooth. On one side of the tooth root, the periodontal ligament is stretched, creating tension. Wolff's Law dictates that osteoblasts migrate to this tension side and build new bone.
And on the opposite side?
On the opposite side, the tooth is being driven hard into the socket, creating sustained pressure. The osteocytes sense this pressure and activate the osteoclast, the demolition crew. They literally dissolve the jawbone out of the way because the bone melts in front of the tooth and rebuilds behind it. The solid tooth can physically migrate through the dense, solid bone of the maxilla or mandible over a period of months.
It is controlled therapeutic bone resorption. Unbelievable. Now, the bones provide the levers, but movement requires those levers to pivot. Where bones meet, we have joint or articulations, and the textbook categorizes them strictly by the degree of movement they permit.
The degree of mobility dictates the structural design. We recognize three broad categories: fibrous joints, cartilaginous joints, and synovial joints.
Let's start with fibrous joints. These seem designed for maximum stability and minimum movement.
They are essentially locked down. In a fibrous joint, the opposing bony surfaces are bound tightly together by incredibly dense fibrous connective tissue. The classic examples are the sutures of the skull.
Right.
The irregular sawtoothed edges of the flat cranial bones interlock like puzzle pieces, united by ultra-short connective tissue fibers. In an adult, they permit zero functional movement, ensuring the brain is housed in a rigid vault.
Another type mentioned is the syndesmosis.
A syndesmosis allows just a fraction of movement. The bones are farther apart and connected by a broader band or sheet of fibrous tissue, such as the interosseous membrane connecting the radius and ulna in your forearm. It allows the bones to slightly shift and rotate around each other, but keeps them firmly tethered.
The second category is cartilaginous joints.
Here, the articulating bones are united by cartilage, lacking any joint cavity. A primary cartilaginous joint, or synchondrosis, uses hyaline cartilage. These are often temporary. A perfect example is the epiphyseal growth plate in a child's long bone. The cartilage allows the bone to grow, but eventually the joint completely ossifies into solid bone.
And the permanent ones.
Those are secondary cartilaginous joints, or symphysis. The articular surfaces of the bones are covered in hyaline cartilage, but they are fused together by a thick, compressible pad of fibrocartilage. They usually occur strictly in the midline of the body.
Like the pubic symphysis.
Yes, or the intervertebral discs between your spine bones. And early in life, the mandibular symphysis, where the two halves of the lower jaw unite. They provide immense strength with a limited amount of shock-absorbing flexibility.
Which brings us to the high mobility hinges. The synovial joints.
Synovial joints are complex, highly evolved structures designed to afford the greatest possible range of motion. They have a very specific architectural checklist. First, the opposing ends of the bones must be capped in a smooth, frictionless layer of articular hyaline cartilage.
Second, the whole thing has to be enclosed.
Yes. The joint is completely enveloped by a tough, fibrous articular capsule that attaches to the periosteum of the participating bones, sealing the joint off from surrounding tissues.
And inside that sealed environment.
The inner surface of that fibrous capsule is lined with a highly vascular synovial membrane. This membrane constantly filters blood plasma to secrete synovial fluid into the joint cavity.
The biological lubricant.
It is much more than just a lubricant. While its extreme viscosity does reduce friction to near zero levels, it is also a vital shock absorber. The fluid actually thickens under sudden pressure, cushioning the joint.
Oh, that makes sense.
Furthermore, because that smooth articular cartilage on the ends of the bones is entirely avascular, it relies 100% on the synovial fluid washing over it to deliver oxygen and nutrients and to carry away metabolic waste.
The text singles out a specific synovial joint for the head and neck.
Right.
The temporomandibular joint, or TMJ. The jaw hinge. And it points out that the TMJ possesses an extra internal structure.
The TMJ is one of the most complex joints in the human body. Because of the immense crushing forces generated by the muscles of mastication, the simple cartilage and fluid setup isn't enough. The TMJ contains an articular disc or meniscus made of tough fibrocartilage.
Sitting right in the middle.
Yes, this disc sits right in the middle of the joint cavity, completely dividing it into upper and lower compartments.
What does dividing the joint achieve?
It allows the joint to perform two completely different types of movement simultaneously. The lower compartment allows for simple hinge-like rotation when you first open your mouth. But to open your mouth wide, the entire lower jaw must slide forward. The upper compartment of the TMJ allows the articular disc and the jawbone to glide forward as a single unit over the skull base. It is essentially a joint that must partially dislocate itself every time you yawn. The disc acts as a crucial sliding shock absorber during that complex biomechanical event.
Okay, so a city with high-powered engines and dynamic scaffolding requires immense logistical support. Let's move to the plumbing and sanitation networks, the circulatory and lymphatic systems.
The cardiovascular system is a massive, closed-loop, pressurized transport network. It consists of a central pump, the heart, and a sprawling highway system of arteries, veins, and capillaries.
Its mandate is relentless.
Absolutely. Deliver oxygen, water, nutrients, and hormones to the distant suburbs and haul away the toxic accumulation of carbon dioxide and metabolic waste.
Let's trace the flow of this loop as the text describes it. The heart is functionally two separate pumps sitting side by side. Let's follow a red blood cell returning from a long trip.
Okay. Your red blood cell, depleted of oxygen and loaded with carbon dioxide, returns from the body tissues and pours into the right atrium of the heart via the massive superior and inferior venae cavae. From the right atrium, it is pushed through the tricuspid valve and drops into the right ventricle.
That's pump number one?
Yes, the pulmonary pump. The right ventricle contracts forcefully, slamming the tricuspid valve shut to prevent backflow, and ejects the deoxygenated blood up through the pulmonary trunk. The blood is routed directly to the lungs. Inside the pulmonary capillary beds, the red blood cell releases its cargo of carbon dioxide and binds to a fresh payload of oxygen.
But the blood can't just meander back out to the body from the lungs. It needs repressurizing. It heads back to the heart for pump number two.
The freshly oxygenated blood returns via the pulmonary veins and empties into the left atrium. It passes through the bicuspid or mitral valve into the left ventricle. The left ventricle is the true powerhouse of the system. Its muscular walls are vastly thicker than the right ventricles.
Because it has to push blood all the way to the toes and up to the brain against gravity.
Exactly. The left ventricle undergoes massive contraction, blasting that high-pressure, oxygen-rich blood out through the aortic valve and into the aorta, the largest artery in the body. From there, it is distributed into the systemic arterial tree.
And the architecture of that tree changes as it branches. The massive elastic arteries split into smaller muscular arteries, which split into tiny arterioles, which split into metarterioles, until we reach the final destination, the capillary bed.
The capillary bed is the entire reason the cardiovascular system exists. Everything else is just transport. The capillaries are the site of exchange. The walls of a capillary consist of a single layer of endothelial cells resting on a basal lamina.
They're tiny, right?
They are so incredibly microscopic that the lumen, the hollow tube inside, is often smaller than the diameter of a single red blood cell.
Wait, if the tube is smaller than the cell, how does the blood get through?
The red blood cells have to deform. They physically fold and squeeze themselves through the capillary in single file. This drastically slows down their transit speed.
Oh, that's clever.
It is. That low velocity, combined with the microscopic thinness of the capillary wall, provides the perfect window of time for rapid diffusion. Oxygen, glucose, and amino acids flood out of the blood and into the tissue spaces, while carbon dioxide and cellular waste diffuse from the tissues back into the blood.
And then the capillaries merge into venules, then veins, returning the waste-laden blood back to the right atrium to start the cycle again. Now, earlier, when we discussed smooth muscle, you noted that the autonomic nervous system commands the blood vessels to dilate or constrict to manage this massive pressurized system.
Yes.
But to make those commands, the brain needs real-time telemetry. It needs sensors. And the text highlights two incredibly important sensors located right in the neck.
For anyone studying head and neck anatomy, the carotid sinus and the carotid body are prime clinical landmarks. They are located on the major arterial highways supplying the brain, and they provide critical negative feedback data to the central nervous system.
They sound similar, but their functions are entirely different. What is the carotid sinus?
The common carotid artery runs up your neck and splits into the internal and external carotid arteries. Right at the very beginning of the internal carotid artery, there is a slight dilation, a swelling in the vessel wall. This is the carotid sinus. It functions as a baroreceptor.
Baro meaning pressure.
Yes. The walls of the sinus are densely packed with sensory nerve endings from the glossopharyngeal nerve. They are mechanically sensitive to stretch. As your blood pressure pulses, the wall of the sinus stretches.
And if it stretches too much?
If your blood pressure spikes dangerously high, the sinus stretches violently. The nerve endings fire a rapid volley of signals up to the brainstem. The brain instantly triggers a parasympathetic reflex, slowing down a heart rate and dilating peripheral blood vessels to drop the pressure back to safe levels.
It's an automated pressure relief valve. And what about the carotid body?
The carotid body is a small oval mass of highly specialized tissue nestled right in the crotch of the bifurcation, where the common carotid splits into the internal and external branches. The carotid body does not care about pressure. It is a chemoreceptor.
It is constantly sampling the chemical composition of the blood flowing past it.
Yes.
What chemicals is it looking for?
Primarily, it monitors the partial pressure of oxygen, but it is also highly sensitive to rising carbon dioxide tension and an increase in hydrogen ion concentration, which means a drop in blood pH acidosis.
So if I'm holding my breath underwater,
Your oxygen levels drop and your CO2 levels spike. The carotid body detects this chemical shift instantly. It fires an alarm signal up to the respiratory centers in the medulla of your brain. The brain responds by forcing a massive autonomic reflex, compelling you to gasp for air and increasing your respiratory rate to blow off the excess carbon dioxide and restore the blood pH.
incredible mechanism.
Yeah.
So that handles the high-pressure water mains of the city. But what about the lymphatic system? The source text presents this as a completely separate, parallel network. If the cardiovascular system is the pressurized delivery grid, the lymphatic system seems like the passive, quiet sanitation and drainage network.
That is an excellent way to frame it. To understand why we need lymphatics, we have to look back at the capillary beds. When that high-pressure blood from the arterioles enters the microscopic capillaries, the hydrostatic pressure literally forces blood plasma to leak out through the thin endothelial walls and into the surrounding tissue spaces.
The plumbing is intentionally leaky.
Yes. This leaked plasma, now called extracellular fluid or tissue fluid, bathes the cells directly, delivering the nutrients. On the venous side of the capillary bed, the pressure drops, and osmotic forces pull most of that fluid back into the blood vessel. But not all of it. A slight surplus of fluid is left behind in the tissue spaces.
But if you leave a little bit of fluid behind in every tissue every second of every day, we would just swell up like water balloons, right?
We would suffer massive systemic edema. This is where the lymphatic system intervenes. Scattered throughout almost all the tissue spaces of the body is a network of blind-ended lymphatic capillaries. They are essentially microscopic, highly permeable vacuum cleaners. They passively absorb that excess tissue fluid, along with any escaped proteins or cellular debris. Once the fluid enters the lymphatic vessel, its name changes. It is now called lymph.
But it doesn't just pipe this unfiltered ditch water straight back into the heart.
No, doing so would be extremely dangerous. The tissue spaces are where bacteria and viruses frequently enter the body. If the lymph dumped directly into the blood, a minor localized skin infection would instantly become lethal septicemia. So, the lymphatic vessels route this fluid through a series of highly organized biological filtration plants.
The lymph nodes.
The customs checkpoints.
Right.
A lymph node is a small bean-shaped organ packed full of lymphoid tissue, which houses massive armies of lymphocytes and macrophages, or white blood cells. As the sluggish lymph percolates through the node, these immune cells inspect it. They actively phagocytose, eat cellular debris and bacteria.
And if they find something bad?
If they detect a specific viral antigen, they mount a full-scale, targeted immune response, multiplying rapidly. This is why your glands in your neck swell up when you have a throat infection. It is the physical expansion of millions of lymphocytes proliferating to fight the war.
And once the lymph is filtered and cleared by these checkpoints,
The purified lymph continues its journey through progressively larger lymphatic vessels, eventually draining into the massive lymphatic trunks at the base of the neck. Here, the lymph finally dumps back into the venous system, returning the lost fluid volume to the cardiovascular loop.
the text mentions one highly specialized function of the lymphatic system that has nothing to do with drainage or immunity. It happens in the gut.
Ah, the lacteals. In the small intestine, the tiny finger-like projections that absorb nutrients contain specialized lymphatic capillaries called lacteals. When you digest dietary fats, the resulting lipid molecules are simply too massive to diffuse across the wall of a regular blood capillary.
So they use the highly permeable vacuum cleaners instead.
Exactly. The lacteals absorb these large fat complexes. The lymph, draining from the gut, turns milky white and is called chyle. It bypasses the liver entirely and travels up through the chest via the largest lymphatic vessel in the body, the thoracic duct, which eventually empties all that dietary fat directly into the venous blood in the left side of the neck.
All roads and all lymph lead to the neck. Which brings us to the final and most complex system in our metropolis, the nervous system, the master integrator. The telecom grid and the command center rolled into one.
Every system we have discussed so far, the contraction of muscle, the remodeling of bone, the dilation of vessels, is entirely dependent on the nervous system to perceive stimuli, process the data, and orchestrate a coordinated response.
Anatomically, we divide it into two territories, right? The central nervous system, or CNS, and the peripheral nervous system, or PNS.
Yes, the central nervous system is the mainframe, the brain securely locked inside the skull, and the spinal cord running safely down the vertebral column.
And the peripheral nervous system comprises the massive network of cables running out to the extreme edges of the body. Specifically, the 12 pairs of cranial nerves that emerge directly from the brain and the 31 pairs of spinal nerves that branch off the spinal cord.
Before we talk about the cables, we have to look at the wire itself, the cellular unit, the neuron. The textbook describes it as highly specialized for irritability and conduction.
In neurobiology, irritability is the capacity to perceive and react to a stimulus, whether that is a photon of light hitting the retina or a chemical neurotransmitter bridging a synapse. Conduction is the capacity to transmit that reaction as an electrical impulse, an action potential rapidly over long distances.
The anatomy of the neuron facilitates this perfectly. You have the main cell body, the soma. The text goes out a very old-school term here, noting the soma contains Nissl bodies.
What is a Nissl body?
It is an archaic histological term. In the late 19th century, Franz Nissl developed a stain that revealed granular clumps inside neuron cell bodies. Today, we know that Nissl bodies are simply massive, dense concentrations of rough endoplasmic reticulum and ribosomes.
Ah, the protein factories.
Yes, because neurons are constantly firing and need to constantly replenish neurotransmitter proteins, their manufacturing machinery is incredibly vast, easily visible under a microscope.
Radiating out from this massive protein factory are the dendrites.
The dendrites are the antenna. They are highly branched, tree-like extensions that receive chemical signals from other neurons or sensory receptors. They convert those chemical signals into electrical potentials and conduct them toward the cell body.
And then, projecting away from the cell body is the main transmission wire, the axon.
A neuron possesses only one single axon. It arises from a specialized, cone-shaped region of the soma called the axon hillock. The axon's sole job is to conduct the electrical action potential away from the cell body, carrying the command to another neuron, to a muscle fiber, or to a gland. Now, if we are running electrical cables all over a wet, salty metropolis, we need insulation to prevent short circuits and signal degradation.
We need myelin. The myelin sheath is a lipid-rich, fatty layer of insulation that wraps tightly around the axon. In the peripheral nervous system, this wrap is created by Schwann cells.
How do they do it?
A Schwann cell physically spirals its own cell membrane around and around a segment of the axon, like a roll of tape. In the central nervous system, a single cell called an oligodendrolia reaches out with multiple arms to wrap several different axons simultaneously.
But looking at the diagrams in the text, this insulation is not one continuous smooth sleeve. It looks like a string of link sausages. There are tiny gaps.
Those microscopic gaps in the myelin sheath are called the nodes of Ranvier, and they are the secret to human neurological speed.
How does leaving gaps in the insulation make the electricity go faster? An action potential is a wave of ion exchange sodium rushing into the cell, potassium rushing out. If an axon is unmyelinated, that exchange has to happen sequentially down every single millimeter of the membrane. It's like walking heel to toe. It's slow.
Okay.
But myelin is an insulator. Ions cannot cross it. Therefore, the ion exchange can only happen at the bare gaps, the nodes of Ranvier.
So the electrical signal skips the insulated parts entirely.
Exactly. The electrical impulse literally jumps from node to node, propagating down the axon at blinding speed. This is called saltatory conduction, from the Latin saltare, to leap. Because of myelin in these nodes, a signal can travel down an axon at up to 120 meters per second.
Wow.
If the brain had to achieve that speed using unmyelinated nerves, the axons would have to be so thick that our spinal cords would be the size of a tree trunk. Saltatory conduction is an elegant solution to space and speed constraints.
Shifting from the micro back to the macro. The brain and spinal cord, this incredibly delicate mainframe, needs extreme physical protection. We know it sits inside the bone of the skull and vertebrae, but bone is hard. You can't just have soft brain tissue grinding against rough bone every time you nod your head.
Absolutely not. The CNS is enveloped in 3 distinct, continuous protective membranes, collectively called the meninges.
The text outlines them from the outside in, starting with the dura mater.
The dura mater translates literally to tough mother. It is exactly that. It is a thick, dense, unyielding sac of fibrous connective tissue. In the skull, its outer layer acts as the actual periosteum, the inner lining of the cranial bones themselves.
Moving deeper, we hit the arachnoid layer.
The arachnoid mater is named for its spider web-like appearance. It is a delicate avascular membrane that lines the inner surface of the dura. Tiny web-like trabeculae extend downward from it.
And the deepest layer, shrink-wrapped to the brain.
The pia mater, the tender mother. This is a highly vascular, microscopic layer of connective tissue that is intimately applied directly to the surface of the brain and spinal cord. dipping deeply into every single sulcus and crevice, guiding the blood vessels as they penetrate the nervous tissue.
Now, between that web-like arachnoid layer and the intimately applied pinna mater, there is a space. And that space isn't empty.
The subarachnoid space. This is perhaps the most critical protective feature of all. This space is filled with cerebrospinal fluid, or CSF. The brain and spinal cord literally float within this fluid bath. It provides profound buoyancy, reducing the effective weight of the brain by 97%, so it doesn't crush itself under its own mass.
And it absorbs shock.
Crucially, yes. It acts as a liquid shock absorber, dissipating kinetic energy before it can tear the delicate neural tissue against the skull.
All right. We've established the hardware. Now we have to decode the software. The text insists on a crucial element of academic rigor here, the functional components of the nervous system. For medical and dental trainees, this is notoriously complex. It's an alphabet soup of acronyms, GSA, GVA, GSE. It can feel like memorizing random letters.
It does feel overwhelming initially.
Huh.
But we must demystify this, because if you don't understand the functional components, you cannot diagnose a nerve lesion.
Yeah.
We are no longer categorizing nerves by where they are anatomically located. We're categorizing individual nerve fibers by the type of data they are carrying.
So we have to break down the naming convention. Every fiber gets 3 tags. First, is it afferent or efferent?
This dictates the direction of traffic. Afferent means arriving. It is sensory data traveling from the body into the central nervous system. Efferent means exiting. It is motor commands traveling out from the brain to the body to cause an action.
Sensory is afferent. Motor is afferent. Got it. Next tag, is it somatic or visceral?
This defines the territory. Somatic refers to the outer body wall, the skin, the skeletal muscles, the bones, and the joints, how you interact with the external environment. Visceral refers to the internal organs, the smooth muscle, the cardiac muscle, the glands, and the mucous membranes, the internal environment.
And the final tag, is it general or special?
General means the sensation or motor function is distributed widely throughout the entire body. Touch, pain, moving a typical skeletal muscle. Special means the function is highly localized and restricted entirely to specific structures in the head and neck. Vision, hearing, taste.
Okay, let's put these tags together into the actual acronyms, but instead of just listing them like a glossary, let's map them to real-world scenarios. I'm going to give you an action, and you decode the fiber type based on the text.
Excellent approach. Let's do it.
Scenario 1. I'm barefoot, and I step on a sharp piece of Lego. Searing pain shoots up my leg. What fiber carries that data?
That is a general somatic efferent fiber, or GSA. It is general because pain receptors are everywhere. It is somatic because the skin is part of the outer body wall, and it is afferent because the sensory pain data is arriving at the brain. GSA fibers carry pain, touch, temperature, and proprioception, the spatial awareness of your joints.
Scenario 2. I eat an enormous, highly questionable gas station burrito. 30 minutes later, I feel a deep, nauseating ache and bloating in my stomach.
That is a general visceral efferent fiber, or GVA. General because stretch and pain receptors exist throughout the gut. Visceral because the stomach is an internal organ. Afferent because the data is arriving at the CNS. It's important to note that GVA pain is often dull, poorly localized, and deeply unpleasant compared to the sharp precision of a GSA pain.
Scenario 3. The brain decides it wants to kick the piece of Lego across the room in revenge. It sends a signal to the massive quadriceps muscle in my thigh to contract.
That command travels down a general somatic efferent fiber, or GSE, general because skeletal muscles are everywhere. Somatic because we are moving the external body wall framework. Efferent because it is a motor command exiting the brain.
Scenario 4. The burrito is moving through my gut. The brain sends an involuntary signal to the smooth muscle in my intestines to increase peristalsis and move it along.
That involuntary command travels via a general visceral efferent fiber, or GVE, general because smooth muscle is ubiquitous. Visceral because we are controlling an internal organ, efferent because it is an exiting motor command. GVE fibers form the entire autonomic nervous system.
Okay, those are the general fibers that apply to the whole body. Now we enter the territory of the head and neck, which requires the special categories. Scenario 5. I look out the window and I see a bird while simultaneously hearing it sing.
You are utilizing special somatic afferent fibers, or SSA. Special because the organs of sight, the retina, and hearing, the cochlea, are highly localized to the head. Somatic because they relate to perceiving the external environment, not internal organ states. Afferent because sensory data is arriving.
Scenario 6. I take a sip of coffee and I smell the aroma while tasting the bitterness.
Those chemical senses are carried by special visceral afferent fibers. or SVA. Special because taste buds and olfactory epithelium are localized to the head. Visceral because these senses are intimately tied to the digestive and respiratory viscera, evaluating what we are about to ingest. Afferent sensory data arriving.
And the final scenario, the trickiest one for students according to the text. I decide to chew my food and I smile because it tastes good. I am voluntarily moving the skeletal muscles of my jaw and my face. But they aren't GSE fibers.
No, they are not. This is a critical point. The muscles of mastication, the muscles of facial expression, and the muscles of the larynx and pharynx are voluntary skeletal muscles. But during embryonic development, they do not form from standard body somites like your bicep or quadriceps. They develop from the branchial arches, the embryonic structures that form the gills in fish. Right. Because of this unique developmental origin, they are granted their own functional category, special visceral efferent, or SVE.
So even though they act like somatic muscles, their branchiomeric history makes them special visceral.
Exactly. SVE fibers carry the voluntary motor commands exclusively to these branchiomeric muscles of the head and neck.
The text explicitly points out a common trap here regarding glands. If I start crying or my mouth waters, making a gland secrete is a highly specific action in the head. Is there a special visceral efferent fiber for secretomotor function?
No. There is no special category for making a gland secrete. The autonomic nervous system manages all glands exactly the same way, whether it's a sweat gland in your foot or a salivary gland in your mouth. Making a tear gland cry is standard involuntary motor control, so it remains categorized as general visceral efferent, or GVE.
Speaking of the GVE fibers, the autonomic nervous system, we need to dive deep into how this automated operating system actually works. We've established that conscious somatic movement uses a single continuous wire. A single neuron originates in the brainstem or spinal cord, travels all the way down the nerve, and synapses directly onto the muscle fiber. But the text states that the autonomic nervous system, the involuntary system, requires a two-neuron chain.
This is the fundamental architectural difference between voluntary and autonomic control. The ANS never reaches its target with a single continuous axon. It always uses a relay station.
But why? Why does the involuntary system need a relay station? Why not just run one wire directly to the heart or the stomach? It seems inefficient.
If the goal was simply pinpoint precision, it would be inefficient. But the goal of the autonomic nervous system is divergence and massive, widespread, coordinated physiological response. Let's trace the architecture to see how it achieves this. The first neuron is called the preganglionic neuron. Its cell body sits inside the central nervous system. Its axon travels out into the periphery and enters an autonomic ganglion.
A ganglion is just a cluster of nerve cell bodies sitting outside the brain and spinal cord.
All right.
The relay station.
Correct. Inside that ganglion, the preganglionic axon releases a neurotransmitter across a synapse to connect with the second neuron, the postganglionic neuron. But here's the critical mechanism. That single preganglionic axon branches wildly inside the ganglion. It might synapse with 10, 20, or 30 different postganglionic neurons simultaneously.
Amplification.
Massive divergence. Those 30 postganglionic axons then exit the ganglion and travel to multiple different target organs. This architecture allows a very small, concentrated signal originating in the hypothalamus of the brain to instantly diverge at the relay station and cause a widespread systemic event like simultaneously dilating your pupils, accelerating your heart, dilating your airways, and shutting down blood flow to your gut.
Which perfectly describes the fight-or-flight response, the sympathetic division of the autonomic nervous system.
The sympathetic system prepares the body for immediate, intense physical action or stress. It prioritizes skeletal muscle, the heart, and the brain at the expense of digestion and maintenance.
But the wiring for this system is bizarre. The textbook refers to the sympathetic system as having thoracolumbar outflow. What does that mean for the anatomy?
It means that every single preganglionic sympathetic neuron in your entire body originates in a highly restricted segment of the spinal cord. They only emerge from the spinal cord between the first thoracic vertebra, T1, and the second or third lumbar vertebra, L2 or L3. That is the thoracolumbar outflow.
Wait, if they only exit from the middle of the back, how does a sympathetic nerve signal get all the way up to my eyeball to dilate my pupil, or all the way down to my foot to make it sweat?
To solve that geographic problem, the body utilizes the sympathetic chain ganglia. Imagine two vertical chains of relay stations running perfectly parallel down either side of the entire vertebral column, from the base of the skull all the way down to the tailbone.
A biological highway.
Exactly. When a short preganglionic sympathetic fiber exits the spinal cord in the thoracic region, It immediately jumps onto this highway via a tiny connecting ramp called a white ramus communicans.
Hmm.
Once inside the chain ganglion, it has options.
What options?
It can synapse right there at that level. Or you can turn and travel straight up the chain to the cervical ganglia in the neck, or travel straight down the chain to the sacral ganglia in the pelvis before it synapses.
It uses the chain as an elevator to reach the correct floor.
Precisely. Once it finally synapses at the correct floor, the long postganglionic fiber exits the chain and travels the rest of the way to the target organ.
And what chemical language does it use to talk to the target organ?
The preganglionic neuron uses acetylcholine at the relay station inside the ganglion. But the long postganglionic neuron, the one physically touching the heart or the blood vessel, releases noradrenaline. That is the chemical that triggers the target tissue to enter the fight-or-flight state.
The text notes one very specific exception to that chemical rule.
Yes, sweat glands receive sympathetic innervation. They activate when you are stressed, but the postganglionic neuron releasing onto them uniquely uses acetylcholine, not noradrenaline. It's an anatomical quirk.
The text also points out a much larger functional exception to the two-neuron rule entirely, the adrenal medulla.
The suprarenal, or adrenal medulla, is a fascinating evolutionary shortcut. It is the inner core of the adrenal gland, sitting on top of the kidney. Embryologically, this tissue develops from the exact same neural crest cells that form the sympathetic ganglia.
So the gland is essentially nerve tissue.
It acts as a highly modified, massive sympathetic ganglion. The preganglionic sympathetic fibers travel all the way from the spinal cord directly into the adrenal gland. They synapse on highly specialized secretory cells inside the medulla.
And these cells don't have axons stretching out to target organs.
No, they act functionally as the postganglionic neuron. When stimulated by the preganglionic fiber, these cells dump massive quantities of their neurotransmitter adrenaline and noradrenaline directly into the circulating bloodstream.
So instead of wiring every single cell for stress, the brain just dumps the stress chemical into the water supply.
Exactly. The blood carries the adrenaline to every cell in the body simultaneously, ensuring a systemic, instantaneous, maximal fight-or-flight surge that standard nerve conduction couldn't coordinate fast enough.
That is brilliant. Okay, so that is the sympathetic accelerator. Now we need the brakes, the parasympathetic nervous system, the rest and digest division.
The parasympathetic system opposes the sympathetic. It returns the body to homeostasis. It slows the heart rate, constricts the pupils, stimulates the salivating and digestive glands, and ramps up the motility of the gastrointestinal tract. It is the system of restoration and conservation.
Where does its wiring originate? The sympathetic was thoracolumbar. The text calls the parasympathetic the craniosacral outflow.
Because the parasympathetic preganglionic neurons only originate at the extreme geographical ends of this central nervous system. They arise from the brainstem, the cranial outflow, traveling within 4 highly specific cranial nerves.
Which ones?
Oculomotor, cranial nerve 3, facial 7, glossopharyngeal 9, and vagus 10. They also arise in the very bottom of the spinal cord, the sacral outflow, specifically from segments S2, S3, and S4.
And do they use a massive chain highway of relay stations like the sympathetic system?
No, the architecture is entirely different. Parasympathetic preganglionic fibers are exceptionally long. They travel all the way from the brainstem or sacrum almost entirely to the target organ before they ever reach a relay station. This synapse in what are called terminal ganglia, which are located either directly adjacent to or literally embedded within the wall of the target organ itself.
So the postganglionic fibers must be incredibly short.
Millimeters long. In the head and neck region, there are 4 highly specific, named terminal ganglia, where the cranial parasympathetic outflows synapses before innervating the salivary glands, the lacrimal tear glands, and the constrictor muscles of the pupil. And unlike the sympathetic system, the parasympathetic uses acetylcholine universally at both the preganglionic synapse and the postganglionic target synapse.
Okay, we have mapped the walls, the engines, the scaffolding, the plumbing, and the command grid. A city of systems. Now let's put me in the hot seat. If I'm a surgical trainee or a medical student trying to synthesize all of this, I need to see it working together. Let's look at a single coordinated action, chewing and tasting a piece of food. How do these systems integrate?
It is the perfect holistic example. To take a bite of food, you must generate movement. The muscular system, specifically the branchiomeric muscles of mastication, provides the immense contractile power to elevate the jaw. But those engines need a rigid lever system, which is provided by the skeletal system.
Right, the mandible, the maxilla, the dense enamel of the teeth, and the highly specialized fibrocartilage meniscus of the temporomandibular joint acting as a sliding shock absorber.
And the food is kept contained inside the mouth by the integumentary system, the specialized resilient mucous membranes of the cheeks and lips.
Meanwhile, the cardiovascular system is operating at high capacity. The external carotid artery branches are pumping a massive pressurized volume of oxygenated blood into the masseter and temporalis muscles to fuel their intense contraction, while the venous system hauls away the lactic acid and carbon dioxide.
And orchestrating this entire symphony is the nervous system. Let's track the specific functional components we just learned. The brain sends the conscious, voluntary command to chew down the mandibular branch of the trigeminal nerve. Because the jaw muscles are derived from the branchial arches, this command travels via special visceral efferent, or SVE, fibers.
As I'm chewing, the chemical molecules of the food dissolve in my saliva and bind to my taste buds.
That chemical sensory data is picked up by the facial and glossopharyngeal nerves, traveling back to the brain via special visceral efferent, or SVA, fibers.
The brain registers that the food tastes delicious, so it needs to ramp up digestion.
The brain reflexively initiates a parasympathetic response. It sends an involuntary motor command down the cranial outflow, synapsing in a terminal ganglion, and traveling via general visceral efferent, or GVE, fibers to the parotid and submandibular salivary glands, commanding them to massively increase secretion, initiating the chemical breakdown of the food. Every system is perfectly harmonized in a single second.
It truly is a breathtaking act of biological engineering, and that brings us directly to the core takeaways from this foundational chapter.
First, the body is organized hierarchically, and that hierarchy is functional. Cells build tissues, tissues fabricate organs, organs harmonize into systems. Second, structure and function are biologically inseparable at every single level of that organization. Form dictates function, and function modifies form. And third, these systems are deeply, inextricably interdependent.
Let's test that interdependence. Let's see if I have actually built the functional mental models we promised at the start of the show. I'll pose the scenarios based on the source text's single best answer requirements, and let's reason through them. Scenario 1. I'm looking at a tissue biopsy under a microscope. The muscle fibers lack any form of striation, they are fusiform in shape, and each has only one centrally located nucleus. And I know the biopsy came from the wall of a blood vessel. What am I looking at?
You're looking at smooth muscle. The lack of striation immediately rules out skeletal and cardiac muscle. The single central nucleus confirms it, as skeletal muscle is famously multinucleated with the nuclei pushed to the periphery. And functionally, the autonomic control of vessel diameter is strictly the domain of smooth muscle.
Scenario 2. A patient presents with a deep laceration on their face. The surgeon notes that the cut has severed muscle fibers that were attached directly into the deep layers of the skin itself rather than attaching to a bone. Which layer of the integumentary system uniquely houses the origins of these specific muscles?
That would be the hypodermis, or the subcutaneous tissue layer. While the muscles of facial expression insert into the dermis, they originate within the deep fascia, bone, or the hypodermis itself. This is the unique evolutionary adaptation that allows us to wrinkle the skin for nonverbal communication.
Scenario 3. A pediatrician is evaluating an infant skull x-rays. The large, flat bones of the cranial vault are still growing and fusing. By what specific biological pathway did these flat skull bones initially form?
They formed via intramembranous ossification, the 3D printing method. The mesenchymal stem cells differentiated directly into osteoblasts and laid down bone matrix without ever creating a cartilaginous middleman. If the x-ray was of the infant's femur, it would be endochondral ossification.
Scenario 4. A trauma patient's blood pressure drops suddenly due to blood loss, but their oxygen and carbon dioxide levels are temporarily stable. Which highly specific sensor located at the bifurcation of the common carotid artery would fail to trigger a compensatory reflex in this specific chemical stable scenario?
The carotid body. The question specifies a drop in pressure but stable chemistry. The carotid body is purely a chemoreceptor. It only monitors oxygen, CO2, and pH. The structure that would trigger the pressure-saving reflex is the carotid sinus, the baroreceptor located at the start of the internal carotid.
Scenario 5. We are tracing the neurological wiring that commands the resting and digesting functions of the body. The parasympathetic nervous system is characterized by which specific anatomical outflow from the central nervous system?
The craniosacral outflow. The preganglionic fibers only emerge from the brainstem via cranial nerves, third, seventh, and IX and X, and from the sacral spinal cord segments S2 through S4. If the question asked about the sympathetic fight or flight system, the answer would strictly be the thoracolumbar outflow.
Final scenario. A surgeon accidentally severs the specific nerve fibers that provide motor innervation to the parotid salivary gland in the cheek, permanently halting its secretion. Which functional nerve component was destroyed?
The general visceral efferent, or GVE component. The salivary gland is a visceral structure. The command to secrete is an exiting motor command, therefore efferent. And crucially, there is no special secretomotor category. Autonomic control of glands in the head is handled by the general visceral efferent system, just like the rest of the body.
We have mapped the metropolis. But before we leave you to ponder the immense complexity of your own architecture, I want to leave you with a provocative final thought. We spent a lot of time discussing the autonomic nervous system, the sympathetic accelerator and the parasympathetic brakes, all controlled centrally by the brain. But the textbook briefly introduces a third, almost alien division of the autonomic system, the enteric nervous system.
Yes. The enteric nervous system is a sprawling, incredibly dense web of neurons that resides entirely within the physical walls of your alimentary canal, your digestive tract, from the esophagus down to the rectum.
Here is the fact that is truly astonishing. The text states that this enteric network contains roughly 100 million neurons. That is roughly the exact same number of neurons as your entire spinal cord. It is so biochemically complex, utilizing the same neurotransmitters as the brain, that even if every single sympathetic and parasympathetic neural connection linking your gut to your brain and spinal cord were completely severed by a surgeon, this second brain in your gut would continue to independently orchestrate the complex mechanical peristalsis and chemical symphony of digestion. It doesn't need the skull's mainframe to function. It reminds us that intelligence and coordination in the human body isn't strictly centralized at the top of the neck. It is literally woven into the very fabric of our living systems.
It is a humbling and brilliant reminder. No matter how deeply we map the anatomy, there is always a deeper layer of profound complexity waiting to be discovered. Here are the details of this episode.
Body systems. Byline. Before we explore the landscape of the head and neck, we must understand the living systems that give it function. Episode description. This chapter steps back from regions and maps the body as a living network of systems, each one specialized, yet deeply interdependent. If Chapter 2 gave us the language of anatomy, this chapter gives us its living context. We begin at the smallest scale, the cell, the fundamental unit of life. Cells organize into tissues, tissues into organs, and organs into systems. This hierarchy is not merely structural, it is functional. Each level represents increasing coordination, a quiet orchestration of purpose. We begin at the smallest scale. From here, the chapter surveys the major systems that shape the head and neck. The integumentary system forms the body's boundary, protective, sensory, and regulatory. It is not just a covering, but an interface between the internal world and the external environment. Within it, layers emerge. Epidermis, dermis, and hypodermis, each contributing to protection, sensation, and adaptation. The muscular system introduces movement. Here, three distinct types, skeletal, cardiac, and smooth, demonstrate how form dictates function. In the head and neck, muscles take on added nuance. Some move bone, others move expression itself. The idea of origin, insertion, and coordinated action begins to take shape. The muscular system introduces movement. Here, three distinct types, skeletal, cardiac, and smooth, demonstrate how form dictates function. In the head and neck, muscles take on added nuance. The skeletal system provides structure and protection, but also serves as a dynamic organ storing minerals, producing blood cells, and adapting continuously to stress. Bone is not static. It remodels in response to the forces placed upon it. The muscular system introduces movement. Here, three distinct types, skeletal, cardiac, and smooth, demonstrate how form dictates function. In the head and neck, muscles take on added nuance. The circulatory system brings flow transporting oxygen, nutrients, and waste. It is both a delivery network and a communication system, linking distant regions into a unified whole. Alongside it, the lymphatic system filters and defends, quietly maintaining internal balance. Finally, the nervous system emerges as the master integrator. It perceives, processes, and responds. Divided into central and peripheral components, and further into voluntary and autonomic control, it governs both conscious action and unconscious regulation. Within this, the balance between sympathetic action and parasympathetic restoration systems reflects a deeper principle: stability through opposition. Finally, the nervous system emerges as the master integrator. It perceives, processes, and responds. Divided into central and peripheral components, and further into voluntary and autonomic control, it governs both conscious action and unconscious regulation. Within this, the balance between sympathetic action and parasympathetic restoration systems reflects a deeper principle. This chapter is not about memorizing systems in isolation. It is about recognizing that every structure in the head and neck exists within these systems, receiving blood, responding to nerves, supported by bone, moved by muscle, and protected by skin. Finally, the nervous system emerges as the master integrator. It perceives, processes, and responds. Divided into central and peripheral components, and further into voluntary and autonomic control, it governs both conscious action and unconscious regulation. Within this, the balance between sympathetic action and parasympathetic restoration systems reflects a deeper principle. Understanding systems transforms anatomy from a static map into a living, dynamic network. Finally, the nervous system emerges as the master integrator. It perceives, processes, and responds. Divided into central and peripheral components, and further into voluntary and autonomic control, it governs both conscious action and unconscious regulation. Within this, the balance between sympathetic action and parasympathetic restoration systems reflects a deeper principle. Finally, the nervous system emerges as the master integrator. It perceives, processes, and responds. Divided into central and peripheral components and further into voluntary and autonomic control, it governs both conscious action and unconscious regulation. Within this, the balance between sympathetic action and parasympathetic restoration systems reflects a deeper principle. Key takeaways. The body is organized hierarchically. Cells, A tissues, ear, organs, E systems. The body is organized hierarchically. Structure and function are inseparable at every level of organization. The body is organized hierarchically. The int.